Good afternoon, everyone. Today we are diving into the Newton-Raphson method, a powerful iterative technique for finding roots of a function. We'll be exploring its formula, visualizing how it works, and we'll even look at a couple of examples. My name is Mason Patterson with Cape Fear Community College and Dr. Hans Chapman's EGR 214 Numerical Methods for Engineers. It's the fall 2023 semester, and this is my final project. The Newton-Raphson method uses the first derivative of a function at a given point, the origin. That is set equal to an initial guess, xi, subtracted by the function of x over the function of x's derivative. Repeating this process gives us a more accurate approximation of the function's root. Looking at this graphically, we have a red line, which is going to be the function, the black line, which is going to be the function's derivative, and the dots along the x-axis are going to be our initial guess, different iterations of that guess, and then we're converging towards the red dot along the red line. That is the root in which we are trying to find. So let's apply the Newton-Raphson method to a function negative e to the negative x minus x. With an initial guess of 0, we find that its derivative is negative e to the negative x minus 1. The root is updated using our formula. Initially, our percent error is high, but after 4 iterations, we converge to a value close to 0.56714 with a very, very small percent error. In contrast, we have a different function here. When dealing with x to the 10th minus 1, the Newton-Raphson method struggles. Converging is a little bit slower. It takes about 40 iterations to reach the acceptable percent error. The graph illustrates our initial guesses of 40 were far from the point of the x-intercept. Here, we can see we start at 0.5. It goes well past the x-intercept, up to 50, and then it works its way back from there. So not quite as efficient as the first example. When forming a Python script in Google Colab for the Newton-Raphson method, odds are high that you'll need to import some files to aid with the mathematical portion of the code. For this example, I took the root of our first example from the book, negative e to the x minus x. For starters, I gave Newton's method a definition, allowing for the input of the function, its derivative, the initial guess, and the number of iterations we wanted to use. In this example, I defined math e for the function as well as the derivatives function. Following this, I defined the equation of our root, which is equal to our initial guess minus the function over its derivative. I then printed the root with the numbers of iterations and plugged in my values for Newton's method definition, the initial guess from the book, and took 4 iterations. Here we got 0.56714, just like we got in the book. The next problem amps it up a bit. Here we have a problem using a drag coefficient for a bungee jumper in freefall. We're given several variables: gravity, velocity, the drag coefficient, and the amount of time falling. Fortunately, the book gave us a function and the function's derivative, some kind of beefier equations here. The hardest part of this was kind of plugging these whole things into the Python script successfully. So we can see that in the next slide here. So for starters, I defined all of our variables: 9.81 for gravity, our 0.25 kilograms per minute, drag coefficient, our free falling time of 4 seconds, and our velocity of 36 meters per second squared. Or pardon me, just per second. The book used an initial guess of 140 for the bungee jumper's weight, which I thought was a really good guess, but when I used a mass of 1, I received a similar result. And I say really good guess because the estimate is 142. So starting at 140, it just seemed a little too close. The next step is where I define the function and the derivative, as we're seeing in the previous slide. The function required the import math file and then working with the tangent and secant in these two larger equations. For the derivative, I sliced it up into 3 terms to make it all fit in the screen. So multiplied term 1 and 2 together and then subtracted term 3, just so it's more legible. The book used a percent error tolerance of 100,000th of a percent and a maximum iterations of 50, which you can see right here. And then next we kind of define for the Newton-Raphson method formula. So here we have, our x root being the m guess is set equal to m guess minus our f value over df value. So m guess is set equal to f of m gas. That way we can use this over and over again as a iterative formula. The following section is an if-then statement using our f value, getting the absolute value of that, and setting that lower than our percent error tolerance of 1/100,000th of a percent over 100 times the absolute velocity of the equation. Pretty much just double checking our work and making sure we're within the guidelines of the problem. Finally, we printed it, got 142.73 kilograms. Pretty big bungee jumper, but there's that. Next, I have the graph. For this one, I did import Matlab and NumPy to get all this on here. Along the x-axis, you can see our different values for our mass, falling between 120 and 160. The y-axis is going to be different output values for our function and the derivative from negative 0.6 to 0.4. We can see here that the blue line there for our function crosses right over at 142, giving us our mass. We can see all the different inputs for the graph, etc. printed. All right. When it converges, the Newton-Raphson method usually requires fewer iterations compared to other root finding methods. This makes it computationally efficient, particularly for functions with well-behaved properties. The adaptability of the method, it can be used to find multiple roots of a function simultaneously, and it can be extended to handle systems of nonlinear equations if you need. Newton's method is not limited to any specific type of function, and it can be applied to a wide range of continuous and differentiable functions. And then lastly, the Newton-Raphson method is not restricted to finding roots of equations only. It can be adapted to optimization problems and solving various types of equations. And finally, I guess in closing, I did use some snips from the McGraw-Hill textbook from Cape Fear Community College for my works cited here. So thank you very much. I hope you enjoyed.